Okay, we're recording. Okay, yeah. So happy Halloween. Okay, where were we last time? So last time we were talking about convex sets, and we said that like if you have a convex set for the braid arrangement in type A, this is really the set of linear extensions of some poset. So more generally, you can think of a convex set as, like for an arbitrary Coxeter group, as some kind of a generalization of the set of linear extensions of a poset. So in this class today, I'm going to, I guess, finish talking about some geometric things, and then we're going to start on chapter 7, which is about enumeration in Coxeter groups. So, I think this will be fine. If I have some positive root beta, I'm going to let dp of beta, so this is the depth of beta, this is going to be the minimum of the set of k such that w of beta is in phi minus for some element w, or maybe I should write w beta instead of w of beta, for some w in w of length k. So another way of saying this is you start with some positive root beta, and imagine you want to start applying simple reflections to it until you get down to a negative root. And this is the minimum number of these simple reflections that you need to use. So for example, the depth of beta is 1 if and only if beta is a simple root. Because if it's a simple root, you can just, so if it's alpha sub s and you apply s to it, then that gives you negative alpha sub s, which is a negative root. But on the other hand, if you have some other positive root that's not simple, you have to apply more than one simple reflection to get it down to a negative root. So we can define yet another poset. This is called the root poset. Is the partial order on the set of positive roots, and it's defined so that a positive root beta is covered by a positive root gamma if the depth of gamma is the depth of beta plus 1. So it's like you're going up one step in depth, and gamma is s beta for some simple reflection s. So I'll draw an example of this in a second, but I'll just mention that the minimal elements of the root poset are just the simple roots. And it's also graded. So the root poset is graded. And its rank function is just depth. Okay. So, okay, here's an example. Let's say we're looking at S5, which is the same as A4. So I'm going to, in order to represent the reflection or the positive roots in sort of a concrete, or I guess in a compact way, let me write, I'll draw a box with like A, B, C, D, where these are some numbers, and I'll write this to mean A alpha 1 plus B alpha 2 plus C alpha 3 plus D alpha 4, where alpha I is just alpha sub SI. Okay, so we have like 4 simple reflections here, and they correspond to the 4 simple roots, alpha 1 through alpha 4. And so if I have a positive root, I can write it as a linear combination of the simple roots with non-negative coefficients. And so I'm just, instead of writing out this whole thing, I'm just going to write A, B, C, D in a box. So what this looks like is, well, at the bottom we're going to have the simple roots, which will be like 1, 0, 0, 0. So that would just represent alpha 1. And then we'll have 0, 1, 0, 0. And then we'll have, let me make sure I'm, yeah, okay. We'll have 0, 0, 1, 0 and 0, 0, 0, 1. So these are just representing alpha 1, alpha 2, alpha 3, and alpha 4. And then above this, so above these two, we'll have 1, 1, 0, 0. And this will be, let me draw actually in other colors. So here I have an edge, and I'll label it by S2. And the reason is because if you apply S2 to alpha 1, you end up getting alpha 1 plus alpha 2. So this is just S2 applied to alpha 1. It's alpha 1. Well, if I wanted to write this out in terms of the bilinear form, remember this is like alpha 1 minus 2 alpha 1 bar alpha 2 alpha 2, and this is negative a half, so this ends up just being alpha 1 plus alpha 2. Okay. So anyway, you can just trust me that S2 of alpha 1 is alpha 1 plus alpha 2. And then here, I'll have this edge labeled by S1, and that's because S1 applied to alpha 2 is alpha 1 plus alpha 2. Then I have, let's say, a green edge here, which will go up to, so this will be labeled by S3. If I apply S3 to alpha 2, I get alpha 2 plus alpha 3. So this will look like this. 0, 1, 1, 0. But I could also, let me do one other color. I guess blue. Oh, actually, okay, so I want this to be orange for S. Oh no. Okay, hold on. Okay, so this is S2. If I apply S2 to alpha 3, I get alpha 2 plus alpha 3. And then I'll also have, this is S3. This is S4. And this root will be 0, 0, 1, 1. And then, okay, there are a few more. So here, above these two, I'll get 1, 1, 1, 0. So that's alpha 1 plus alpha 2 plus alpha 3. Here I want alpha 2 plus alpha 3 plus alpha 4. And then at the very top, I'll get just alpha 1 plus alpha 2 plus alpha 3 plus alpha 4. and I should write down the edges. So here, this is S2. Here, this one is S4. This one is S1. This one is S3. This one is S1 here. And this one is S4. So this is the root poset of type A4. Okay. So in general, this is going to look like basically sort of a triangular shape. It's kind of like a mountain. And I'll just state this fact, which, well, I can sort of justify pretty easily. So the order ideals of the root poset of type A sub n minus 1 are in bijection with Dicke paths of size 2n. So the correspondence looks like this. Let's say we're back in A4. So maybe instead of drawing it like this, I'll just draw it sort of with vertices representing the elements, and I won't label them. So this is this poset, but without all the decorations on it. And I can, if I take some order ideal of this, so maybe I take like this order ideal consisting of these elements like this. Those 6 red elements. Then I can get a Dicke path by doing the following. So I sort of want to draw it like this. This is like one step up, then I go up again. It's kind of hard to draw this. Okay, so I go up, up, then I go down, then I go up, up, down, up, down, 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 like that. And so this is some Dicke path of length 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which is 2n, because this is, so here n is 5, because I'm looking at the root poset of type 5 minus a sub 5 minus 1, and so my Dicke path has length 10. And so this is the correspondence. So at one point, there was a p-set problem, maybe on the 3rd p-set, which I think not everyone has turned in actually now that I think about it, but anyway, here's the solution. So like the, yeah, so you were asked to show that when you take the set of Dicke paths of size 2n and you order them basically by saying that one Dicke path is less than another if it lies weakly beneath it, you want to show that this is a distributive lattice. Well, that's basically because that is just the lattice of order ideals of the type A root poset. Right, so if I have another Dicke path that lies weakly above this, that would just correspond to saying that the order ideal for that Dicke path contains this red order ideal that I've drawn. So I'll just say that this Dicke path lattice that I defined is really J of this lattice of order ideals, or sorry, J of the type A root poset. Let me give a name to this. So let's call the root poset of W, let's call it phi plus of W. So it's kind of a misleading name, but hopefully that's okay. So it's just the set of positive roots, but like thought of as a poset. So as a consequence of this, the size of the lattice of order ideals of the type A, so n-1 root poset, or do I want A sub n-1? I think I want, this is the, oh yeah, this should be Catalan number. Which I called cat of Sn, although this would be the same as cat of An-1. So here's a kind of weird fact. Well, remember I defined Coxeter group, or I defined Catalan numbers for other Coxeter groups. And I said that one way, for example, that you could do this is to look at the non-crossing partition lattice. So I said you choose a Coxeter element, you look at the interval between the identity element and the Coxeter element in the absolute order, and that's this non-crossing partition lattice. And the size of this lattice, first of all, doesn't depend on the Coxeter element, and it's equal to this Catalan number, which you can then define in that way for any Coxeter group. But it turns out that this is also equal to the size of this lattice of order ideals. So if W is a finite irreducible Coxeter group, then if you look at the lattice of order ideals of the root poset of type W, the size of this is the W Catalan number. Now in type A, so in case of symmetric groups, you can find a bijection between dict paths and, say, non-crossing partitions, and this sort of gives a bridge between the non-crossing partition definition and then this definition in terms of like lattices of order ideals of the root poset. But in other types, it's very not obvious how to construct a bijection in sort of a uniform way. You might want to say, like, okay, we want some uniform bijection that we can define and produce and like prove that doesn't really depend on like the classification of finite irreducible Coxeter groups. We just want some Coxeter theoretic description of how to go between the non-crossing partition world, where we have these Catalan objects, and then this world of the order ideals in the root poset. But this is really not obvious how to do this, and actually only in the last few years has there been sort of a satisfying answer to how to get this kind of uniform bijection. Maybe I should draw one other example of the root poset. Let's do it in type S3 tilde. Yeah, so I'll just write it here. This will be affine type S3. And again, I'll write, so here there are three simple reflections. So I'll write A, B, C instead of A alpha 1 plus B alpha 2 plus C alpha 3. And so here's what this looks like. Well, it's going to be infinite, because in this case there are infinitely many positive roots. But I can draw sort of the bottom of it. Okay, let's see. So we're going to have at the bottom 1, 0, 0. and 0, 1, 0, and 0, 0, 1. Here we'll have 1, 1, 0, 1, 0, 1, 0, 1, 1. This will be 1, 1, 2, 1, 2, 1. Wait, is that right? That seems, maybe that's okay. Yeah. 2, 1, 1, 1, 2, 2, 2, 1, 2, 2, 2, 1. And the edges will look something like this. So these are all S2. And there are edges for S1. And then for S3. Oh, I missed some. Wait, yeah. So I missed one here. Okay, so that's what this looks like. Any questions about this? It's almost odd. Okay, so now we can start on enumeration. Which basically means that we want to count things, which I guess is what you would expect in a combinatorics class. So in particular, let's suppose I have some subset A of my Coxeter group W. So W is some Coxeter group. Then I want to define A of Q. So Q is some variable. This will be the sum over all elements little w in my Coxeter group W of Q to the power of the length of W. So W might be infinite, so this could be an infinite sum, but that's okay, because there are only finitely many elements of each possible length. Well, okay, maybe I should assume, as I've been doing, that there are only finitely many simple reflections. So I guess we're assuming that S is finite. Okay. So in this case, there are only finitely many elements of each given length, so this will be some well-defined power series in the variable Q. Or if W is finite, this is just a polynomial. Okay, and so we want to, oh, sorry, I missed, okay. This should be an A. So A, yeah, A is a subset, and if I write A of Q, I want to sum over the elements of A. And what we're interested in is just the case when A is all of W. So we want to compute W of Q, which is just where I'm summing over all the elements of the Coxeter group. So to start, we can kind of reduce to looking at irreducible Coxeter groups. So lemma, if we have a Coxeter group which is a direct product of a bunch of smaller Coxeter groups. By that I mean like the Coxeter system is a direct product. So if W is, let's say, W1 cross dot 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 cross WK, so this is a direct product of Coxeter systems. Then, well, W of Q is just going to be the product from I equals 1 to K of W sub I of Q. Okay, and the proof of this is pretty easy. Yes?
So, like, on the very left, when you say with LK, do you mean like with, like, L of W is K?
Yes, sorry. Yeah, that was wrong. With length of W equals K, yes. Thank you.
Thank you.
Okay. The beginning of class was kind of hectic. So-
Sorry, that's my fault.
No, I mean, it's also my fault. It's Hadling's fault. Okay. So what does an element of this Coxeter group look like? Well, it's just a K tuple of elements of these smaller Coxeter groups. So if W, my little w, is W1 through WK, right, where Wi is in capital Wi, well then the length just adds. So the length of W is the sum from I equals 1 to K of length of Wi. So this means that W of Q is going to be the sum, well, okay, it's the sum over all W in W of Q to the length of W. That's just the definition. But I could write this as sum over W1 in capital W1, dot dot dot, sum over WK in capital WK of Q to the, well, the length is just going to add, so you get length of W1 plus dot 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 plus length of WK. And then this just factors into, right, this is just going to be the product from I equals 1 to K of the sum over, Wi in capital Wi of Q to the length of Wi. So this is just what we want. Okay. So all this means is that if we're wanting to compute this generating function W of Q, it suffices to consider that the case in which W is irreducible. So here's another lemma, which is a little bit less trivial. So let's say we choose some subset J of our set of simple reflections. Then what we can do is write capital W of Q as W superscript J of Q times W sub J of Q. Where, remember, W sub J is the parabolic subgroup generated by J, and then W superscript J is this parabolic quotient corresponding to this parabolic subgroup. And so here I'm using this notation that I had before, where A is just some subset of the group, and I'm using it for these. So the proof of this is so we have, okay, well, W of Q is, again, by definition, the sum over W and W of Q to the length of W. But if I take some element W, remember there's this unique way of factoring it into an element of the parabolic quotient times an element of the parabolic subgroup. So this is sum over W and W of Q to the, and this factorization was length additive. So the length of W is the length of W sub, or maybe I should write, yeah, the length of W sub j plus the length of W superscript j, where these are little w's. But here I could just write this, because this is like a unique factorization, I could just factor this sum, or I could write it as like sum over W sub j in capital W sub j of Q to the length of W sub j, and then times the sum over W superscript j in W superscript j of Q to the length of W superscript j. And this is exactly what we want, because this is exactly that, and this is exactly that. Okay. So why is this helpful? Well, W subscript j is a different Coxeter group. It's just like a smaller Coxeter group. So if we are trying to compute these things, we could do some kind of inductive approach where we say, well, in order to compute W of Q, we could just try to compute W subscript j of Q, which is it's like a similar thing, but for a smaller Coxeter group. The only issue is that this W superscript j is not a smaller Coxeter group. It's like this parabolic quotient thing. So maybe I'll write this down. So to compute W of Q, we just need to compute W subscript j of Q and W superscript j of Q for some j. Well, this is only going to be helpful if j is not empty and not all of S. So for some non-empty proper subset j. And as I was saying, since W subscript j is a Coxeter group, we can assume inductively that we have computed W subscript j of Q. And then the only issue is that W superscript j is not a Coxeter group. So let me just recall some notation that we had a while ago. So we said that the script d sub I superscript j is the set of all elements W in the Coxeter group, such that the right descent set of W contains I and is contained in J. And then we also just said this script d sub I without a superscript is just the set of elements with right descent set exactly equal to I. So this would be dii. And then, well, what was this parabolic quotient, Wj? Concretely, it was just the set of things whose right descent set is contained in the complement of J. Okay? So here's a proposition. Wondering if I should use a different. Yeah, because my chalk broke. Oh well. Proposition. So if I is contained in J, the subset of the set of simple reflections, then we have we can write di superscript j of q. This would be this generating function, but now we're summing over the elements whose right descent set is contained in j and contains I. This is going to be equal to the sum over all sets k that are, so that I want them to contain j minus I and be contained in j. And I'm going to take -1 to the power of the size of j minus k. And then I'll take this thing. So this is the parabolic quotient coming from the set S minus k. So here's a proof. Well, for each set k, we have if we take this parabolic quotient W S minus k of Q. Well, okay, so what is this? This set, if I don't think of the Q, if I just look at this set of elements of the Coxeter group, it's the set of things whose right descent set is contained in the complement of S minus k. In other words, it's the set of things whose right descent set is contained in k. So if I'm summing up over all of those, then that's really the same as just taking the sum over all sets L contained in k of d sub L of q.
Sorry, Colin?
Yes?
When we're writing DJ of IQ, like what are we grouping by?
When we write this, what are we what?
What are we grouping by?
So this is some subset of the Coxeter group.
Oh, so it's that same.
So it's the same thing as over here where I had the A. I'm just summing over all the elements of this set.
Oh, okay.
And for each one, just taking q to the length of the element.
Okay, cool.
Yeah. So here, I mean, this is summing up over all things whose right descent set is contained in k. So I'm just taking the sum over all subsets of k, and then this is the sum of all things. It's the sum over all the things whose right descent set is exactly that subset. Okay? So thus, okay, we can just compute some things. So I want to look at this sum that I've written down. Sum over j minus I contained in k, contained in j of -1 to the size of j minus k, W S minus K of Q. This is equal to sum over J minus I contained in K contained in J of, okay, well, -1 to the size of J minus K. But now I can write this as this thing. So sum over L contained in K of dl of Q. And now I can rearrange the sum. So instead of summing over all K and then summing over all L, I'm going to say, well, this is the same as taking my sum over all L contained in J, and I'll take the dl of Q. And then I want to sum over all K such that, okay, let me write it here. So I want to sum over all K contained in J, but K must also contain J minus I union L. Okay. So it looks a little weird. I'll write what the sum is over. Well, okay, it's just -1 to the size of J minus K. So all I did here is say, instead of summing over these K and then summing over the L, I'm going to sum over the L and then sum over the K that have to satisfy whatever the appropriate condition is. Okay. So then we can use the principle of inclusion-exclusion. Basically to make sense of what this alternating sum is. So by the principle of inclusion-exclusion. Well, the principle of inclusion-exclusion basically says that if we take a sum like this, so we take the sum over, well, this weird condition J minus I union L contained in K contained in J of -1 the size of J minus K. I should say this is really the same as taking -1 to the size of K, but maybe minus that depending on the parity of J. But that might be a better way to think about it. This is basically 1 or 0, and it's 1 precisely when these two sets are the same. So, yeah, so this is 1 if J minus I union L equals J, and it's 0 otherwise. Do you agree with this, or should I say more about this? This is sort of just, I guess, a different way of thinking about, I mean, I don't know the way that you've learned to think about the principle of inclusion-exclusion, but this is just one way to phrase it. So, well, okay, this thing that I wrote down, let me not write it again, I'll just draw an arrow. This thing is equal to, well, okay, I only get a contribution here when J and this set J minus I union L are equal, otherwise I just get a 0. So I only have to care about the case when J minus I union L is J. And the point is that is equivalent to saying that L, so I'll just write it down, This is equivalent to saying that I is contained in L is contained in J. Right, because if I have this, then I'm saying that if I take J minus I, but then I union it with L, then I get everything back from I, right? It's like I've taken J, I've removed I, but then I add back L, so I'm going to get everything back from I, so I end up just getting J. So this condition here is equivalent to saying this. Oh, sorry, to saying that J minus I union L equals J. And so I just have to do this sum. And finally, this is just what I want, which is dij of q. Because, right, that's exact. So dij of q is just the set of elements whose right descent set is contained in J and contains I. So here I'm just saying for each subset, I just take the sum over the things whose right descent set is exactly that subset. Does this make sense, or should I explain something here? Okay, so now we get a corollary. Actually, I can probably write the corollary here. So first of all, if W is a finite Coxeter group, then if I look at this sum, I'm going to sum over all k, a subset of S, of -1 to the k, sorry, to the size of k, divided by W sub k of q. So I'm summing over all subsets, and for each one I take this -1 to some power divided by the generating function corresponding to the parabolic subgroup generated by k. This will end up being q to the length of the long element W naught divided by the whole generating function that I actually care about, which is W of q. And if W is infinite, then I can write down the same sum, and it's 0. Maybe I'm going to switch to orange since my white chalk is broken.
I have X. Do you need chalk?
Oh, is it the Hagoromo?
Yeah.
Oh, okay. Thank you. Thank you. I'll try not to break it. Okay, so here's the proof of this. So let's just put I equals J equals S in the proposition that I just proved. So if I do this, then I get, so dSS of Q divided by W of Q. What is this? So this is going to be the sum. Right, so here I'm looking at this. I'm just taking I and j to both be s. So dss of q is going to be the sum over all k which are contained in S, and contains, well, S minus S, which is the empty set. So this is just saying I'm summing over k contained in S. Of -1 to the size of S minus k. So I'm just plugging in there. And then I also want this thing, W S minus k of q. But then I'm going to divide by W of q. So W S minus k of q divided by W of q. Okay, so it's just this thing, but with I equals j equals s, and then I divided each side by W of q. And well, what is this thing? Well, it's the sum over k, a subset of S, of -1 to the size of S minus k. And then this is, so here I'm taking this parabolic quotient and dividing by the full thing, W of q. But if we go back to this lemma that we have, I'm basically saying, well, it's this thing, but with j being replaced by S minus k. And I'm dividing it by that. So that should be the same as 1 over the generating function that I get for the parabolic quotient. So all I'm doing is using this lemma here to say that this is the same as, that this fraction here is 1 over W sub k, or no, sorry, it's W sub S minus k of q. But we can simplify this a little because here I'm summing over all subsets, and then the thing in the sum is like S minus that subset, but I might as well just take complements and just sum over k and just take the k in here. So what I mean is this is the same as this. Right, so all I did is just say replace S minus k with k. So go from here to here. And okay, so I have this now. And now if I want to prove part 1 in this corollary, I just say, so for 1, just note that, well, what is ds s of q? In this case, W is finite, so I'm summing over all elements whose right descent set is exactly the entire set of simple reflections. Well, there's only one element whose right descent set is the entire set of simple reflections, and that's the long element. So in this case, I'm really just, this is just going to give me q to the power of the length of the long element. So if I plug this in, then I get that this, which is what I want, is q to the length of the long element divided by W of q. So that proves this part 1. And then for 2, we just note that dss of q is 0 if W is an infinite group, because in an infinite group there are no elements whose right descent set is the entire set of simple reflections. Any questions about that? Okay, so one reason this corollary is nice is because it actually allows us to compute W of q. So I'll give an example. So say I want to compute, in the case when W is the hyperoctahedral group B2. So just remember that the Coxeter graph looks like this. So I'm calling the simple reflections A and B here, I guess. So in this case, the length of the long element is, well, what is the long element? It's just A, B, A, B in this group, which is also B, A, B, A. So the length of this is 4. So if I use this corollary, I can say Q to the 4th divided by W of Q is, well, okay, so I want to sum over all subsets of my set of simple reflections. There are only 2 simple reflections, so I'm just summing over, like there are only 4 subsets. And for each one I take this thing. So if I write down what that is, I should get, well, it's 1 over W sub empty of Q minus 1 over W sub, so let me just write WA of Q. I guess technically what I should be writing is A with little curly braces around it because it's the singleton set A, but whatever. And then minus 1 over WB of Q, and then plus 1 over all of W of Q. So this corresponds to choosing K, my subset, to be the empty set. This is when K is just the set A. This is when K is just the singleton set B, and this is when K is both simple reflections. And we can figure out what this is. Okay, 1 over, so W sub empty set of Q. So W sub empty set, this is just going to be the parabolic subgroup generated by the empty set, so it's the identity element. So we're just summing over the identity element of Q to the length of the identity element, which is just Q to the power of 0, so that's 1. So here, this whole thing is just, this fraction is 1. What is W sub A of Q? Well, okay, this is the parabolic subgroup generated by just the element A. And so that's just going to be a 2-element group. It just has the identity element and A. And so if I take my generating function, I'm just taking Q to the length of the identity plus Q to the length of A. So that's just 1 plus Q. Okay, so that's what this is. And similarly, this is also 1 over 1 plus Q. And then this is 1 over W of Q. But now we can solve for W of Q. So I guess I just wrote this down. I think what you end up getting is that W of Q is 1 plus Q divided by Q to the 4th times 1 minus Q. Or sorry, maybe Q minus 1. Okay. So we can do a maybe slightly more difficult example. I mean, it's not difficult, it's just a little more involved. So let's say W is this Coxeter group here. Has this Coxeter graph. I'll call this A, I'll call this B, I'll call this C. This edge will be 4, and these, let's say these are both 3, so I won't write the labels. So in this case, W is infinite. So if I apply the theorem, then I should say that 0 is this sum. So if I write down what the sum is, I get 0 equals, well, again, I want 1 over W sub empty of Q minus 1 over W sub A of Q minus 1 over W sub B of Q, minus 1 over W sub C of Q. But then I'm going to add 1 over W sub AB of Q, and by this I just mean, like, this is the set A comma B. And then I'll add 1 over W sub AC of Q, and then I'll add 1 over W sub BC of Q, and then finally I'll subtract 1 over W of Q. So we can figure out what these are. Okay, so 1 over W sub empty set of Q as before is just 1. And as before, these are just going to be, each one is just 1 over 1 minus Q, or sorry, 1 plus Q. So minus 1 over 1 plus Q, minus 1 over 1 plus Q. Okay, so what is W sub AB of Q? Well, AB, if I just look at the parabolic subgroup generated by A and B, that's a copy of B2. Right? Like if I ignore the C, I just get this thing. So I already computed what its generating function should be. It's this. So 1 over W sub AB of Q is just 1 over this thing. So I should get just the reciprocal of this, which is Q to the 4th times Q minus 1 over 1 plus Q. Sorry, there should be a plus sign. And then, well, what is W sub AC? Well, if I ignore the B, W sub AC is just, this is just the symmetric group A2, or in other words, it's a copy of S3. And I could just write down what the generating function of that is by just thinking about, well, there are 3. You could use this process to figure out what W sub AC of Q is, but I could also just write it down like this. It's 1 over 1 plus 2Q plus 2Q squared plus Q cubed. And this is just because there's the identity element, which has 0 inversions. There are 2 elements with 1 inversion. There are 2 elements with 2 inversions, and there's 1 element with 3 inversions. So here I'm just like writing down what the generating function is sort of explicitly. And then also, W sub BC is also just the symmetric group A2. So I get the same thing. 1 plus 2Q plus 2Q squared plus Q cubed. And then finally I subtract 1 over W of Q. And the whole point is that now I have some equations. 0 equals some stuff that I've written down explicitly minus 1 over W of Q. And from this you could solve for whatever W of Q is. I think you end up getting, well, it doesn't really matter what it exactly is, but I can write it down. So solving this W of Q is 1 plus Q, 1 plus Q squared, 1 plus Q squared plus Q cubed divided by 1 minus Q squared minus Q cubed minus Q to the 4th plus Q to the 6th. Okay. So I guess the point is that using this corollary here, you can basically compute, just recursively, you can compute W of Q for any Coxeter group. So this sort of solves this problem, except there's one thing you might notice, which is like the answer we get here is very nice. And you might also remember from like P set 1, I said show that when you look at just the symmetric group, so actually I'll just say recall. So this is the end of the example. So recall that if W is AN, or the symmetric group Sn plus 1, then W of Q was the product from I equals 1 to n of 1 minus q to the I plus 1 over 1 minus q. And I can rewrite this as the product from I equals 1 to n. So I'll write it as bracket I plus 1 sub q. And this notation is, so where I'll write bracket k sub q for what's called the q analog of the number k. And this is just 1 minus q to the k over 1 minus q, which you could also write out as just 1 plus q squared plus dot 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 plus q to the k minus 1. This is called the q analog of the number k. So q analogs are pretty common in enumerative and algebraic combinatorics. Basically, it's some generating function such that if you set q equals 1, you get the original thing that you cared about. So like maybe you care about the number k. This is a q analog of the number k because if you set q equals 1, you just recover the number k. But it's like some generating function that is like a refined version of the number k. You could write down q analogs of like factorials. You can write down q analogs of Catalan numbers, and so people have studied q analogs a lot. In fact, actually, I think I mentioned at one point, like, there's sort of this joke that if you go to an algebraic combinatorics conference, then like the canonical question that you're supposed to ask at the end of the talk, one of them is like, okay, what happens in type B? Because usually they'll say like, something about the symmetric group or dict paths or like combinatorial objects, and so you raise your hand and you say, oh, what happens in type B? Like if you replace the symmetric group by the hyperoctahedral group. The other canonical question is there a q analog? So like, is there some way of inserting q's into the picture to get some refinement of whatever enumerative thing you've done? So anyway, I guess I'm almost out of time, but I'll just say that here we're noticing that like the answers we're getting are actually nice. And so I think next time I will start talking about sort of like why they're nice and a theorem that explains this, although I don't think I'll prove the theorem. And then I'll talk about some other enumerative stuff. So yeah, I guess that's all for today.